Well, we're getting into weather, and so I'm going to be paying a bit more attention to what's going on around us. And this is a weather map from the 0Z soundings. In other words, the soundings, the balloons that were launched yesterday evening at 8 p.m. here would be 0Z Greenwich time. And each of these little clusters of data represents a balloon that was launched. And this is the 500 millibar map. So when data is analyzed above the Earth's surface, it's normally done on constant pressure surfaces. It's not exactly constant altitude, but it's more or less a flat horizontal surface. And what's contoured in black is actually the altitude itself. So that constant pressure surface is a little bit rolling. But the thing to understand is that the level of constant altitude on a pressure surface is very much analogous to an isobaric curve on a level surface. So you can think of these as isobars, these heavy black lines. The temperature, lines of constant temperature, the isotherms, are in the dashed blue lines. But the data from which it is all derived are these little clusters. So there is to the right of the symbol is the altitude of the 500 millibar surface with 1 0 left off. So that at that station, the 500 millibar surface is 5,870 meters above sea level. The temperature is 27 Celsius, and the dew point is minus 11 Celsius. So each of those balloons, as they cross that surface, you have the data there, and then the contours are laid on by the computer. The winds are given too in a little wind barb, using the convention of a short feather being 5 knots, a long feather being 10 knots, and a thick feather like that being 50 knots. So we're talking about geostrophic balance, and I showed you a diagram like this last time, but I wanted to bring it up to date by showing you the current one. So this is the soundings again from last night. It shows this rather interesting little circular pattern over the East Coast. And if you look at these values, 560, 550, I guess 549. So this is a low pressure center. So this would be called a cyclone. It's not at the Earth's surface necessarily. It's at it's about 5 kilometers up in the atmosphere, but that would be a cyclone. So higher pressure around it, lower pressure in the center, and just like we derived theoretically, the winds go counterclockwise around that because we're in the northern hemisphere. And notice how well the winds parallel the isobars. And so these conclusions followed from the geostrophic balance assumption. And the closer the isobars are together, the stronger the wind will be. Here's another system over the west coast, a strong jet stream coming up here, winds reaching to about 65 knots where the isobars are closer together, and then where the isobars are further apart, the winds are considerably weaker. So those general rules about geostrophic balance are seen to hold on this kind of a diagram. Are there any questions on this one before I go back to the main lecture? So these maps are easy to find, and I encourage you to check in with them from time to time to see what's going on. Let me just get rid of this and go back to where we were. Yeah, let me just go back for a second. So we're in the geostrophic discussion. I showed you these little bullet points about a geostrophic force balance. These formulas we went through. This is the map that I showed you last Friday. This was from that moment. And of course, things have changed a bit between now and then. It may be that that same trough is the one that slid east and become a cutoff cyclone the way we saw, or maybe some other thing happened between the two dates, but I suspect it's just that slid over to the east and filled out to form a full round cyclone the way we saw. I think I ended with this one, which was just an example of an isobaric map at the surface of the Earth. These values are sea level pressure, so wherever the pressure was measured, it was reduced to a common altitude, sea level, and then the contours were laid on it. So you can use this to analyze then. And here we had an anticyclone and a cyclone. There are no winds given on this, but now, knowing the geostrophic law, we can say quite a bit about this. The only problem is that this is down close to the surface of the Earth, or in some cases even below the surface of the Earth. It's kind of a fictitious, there's no, these mountains are 1 kilometer or 2 above sea level, so producing a sea level map is a little bit odd for that, but that's okay, we can still interpret it. But the other problem is that when you're right down near the surface of the Earth, there is some friction added to the winds as well. And that will break the geostrophic constraint. Maybe not too badly, but it'll break it a little bit. What tends to happen when you're near the surface is that the winds, instead of blowing right along the isobars, tend to rotate in a little bit. So they're mostly going along the isobars, but they're crossing it a little bit from high pressure to low. So the winds tend to rotate a little bit like that. That's something, that subject is called the Ekman layer. The Ekman layer is a description of how those winds turn in the boundary layer. And when you're analyzing your pilot balloon data in the lab, in lab number 2, you might find some hint of that, some rotation of the wind in the boundary layer due to that breaking of the geostrophic law due to friction. So keep, you may not see it or you may see it, but keep an eye open for it in that data that you're analyzing from your data from the pilot balloon launch. So what more can I say? Well, we're going to be talking about mid-latitude cyclones probably next time, and this is an example where, in addition to sketching in the isobars, they've also drawn in their interpretation of where the cold fronts and the warm fronts are on this particular day. But that's more of an interpretive thing. The isobars are just cut and dried. If you know the pressure data, you can contour those in. If you expand out to look at most of the northern hemisphere, you can see that at any given time, there are lots of highs and lows, cyclones and anticyclones. And again, no wind is given on this, but you can get a pretty good idea of what the wind is. Each one of these lows has a wind going around this way. Each one of the highs has a wind going around that way. And the speed of the wind is related to the packing of the isobars. So the mid-latitude and high-latitude atmosphere is just loaded with these eddies. And one of their jobs is to pump heat northward to balance the heat budget of the high latitudes and low latitudes, which I spoke about last time. If you go to the southern hemisphere, here's Australia. Of course, now everything is backwards because the Coriolis force is reversed in the southern hemisphere. It acts to the left of the motion vector. And so those relationships that we derive have to be reversed also. So here is a low pressure center. We would call it a cyclone. And the sea level pressure is given there, 968 millibars, 976, getting higher as you go away. And they've indicated the arrow here indicating the direction of circulation. And indeed, it is clockwise. So the circulation around this cyclone is opposite to what it would be if we were in the northern hemisphere because the Coriolis force has a reversed sign. And again, if you look at a larger map with the southern hemisphere, here's Antarctica, Australia, Cape Horn, Cape of Good Hope, filled with highs and lows. And again, all the circulations are the opposite to what they would be in the northern hemisphere. So A few things to finish up the discussion. I wanted to mention these 4 items and also see if you have any questions. So try to think up some questions before we finish this subject. First of all, geostrophic adjustment. It's fine to claim that the Earth's atmosphere is in geostrophic balance most of the time, but I think an even more fundamental question is, how does it come to be in geostrophic balance? And that process is called geostrophic adjustment. And one way to imagine it, but you can do these calculations on your own, is to imagine you've got some isobars drawn on a map. In this case, they've been drawn east-west, and they've been labeled with pressure. And let's assume at the beginning moment that you've got a parcel of air sitting there not moving. Well, you know that's not in geostrophic balance because it's in a region that has a pressure gradient, so it's going to have a pressure gradient force, but if it's not moving, it can't have a Coriolis force, so those 2 forces cannot possibly be in balance. So here's your parcel not moving. I release it, and it's going to immediately feel the pressure gradient force pushing it towards the north. It's going to start to accelerate in that direction. So as the minutes and hours tick by, it's going to, starting with 0 speed, it's going to have then maybe 1 meter per second, 2 meters per second, 3 meters per second. But now as it picks up speed, it's going to start to feel a Coriolis force. Small at first, because remember, the Coriolis force is proportional to the wind speed. So after some time, it may have moved to here and will have developed a little bit of Coriolis force, and it'll start to turn. Coriolis force is a deflecting force. It'll start to turn. Throughout all this time, however, because I've drawn these isobars equally spaced, the pressure gradient force on that parcel will remain the same. So it's always being pushed to the north by the pressure gradient force, but as it moves and accelerates, it turns and accelerates and eventually ends up moving east with a speed that will give it an equal and opposite Coriolis force and pressure gradient. So that process of geostrophic adjustment usually takes about 12 hours in the atmosphere. Parcels could be disturbed by getting caught up in a thunderstorm. They could be disturbed by running against a mountain range and being deflected, running against a building and getting deflected. But then as the hours pass, it naturally tends to want to return to a state of geostrophic balance. It's a natural tendency in the atmosphere for the wind to try to readjust itself to geostrophic balance. What you might do is leave a couple inches in your notes and either redraw the isobars with some other orientation and repeat the experiment, or to be even more confusing perhaps, start that parcel off in some arbitrary direction and imagine what's going to happen to it. If you start it off with some speed, it's going to have a Coriolis force, but it's going to be in the wrong direction for geostrophic balance. Then follow that parcel just with your little sketch and see how it is that it loops around and eventually reestablishes geostrophic balance. It'll always get there. No matter what direction you start that parcel, it'll loop around in such a way that it'll eventually end up in geostrophic balance. So do some practice on that. Any questions on this process of geostrophic adjustment? Same thing happens in the oceans, by the way. The Coriolis force acts on ocean currents, and ocean currents are even in a more rigorous state of geostrophic balance than is the atmosphere. So these same principles we're learning now apply to ocean currents as well. It's ironic that this Coriolis force, which is so small that we don't notice it in our everyday lives, yet has this kind of dominant force on a larger scale. Yes?
What are the arrows going up and down and then right by airflow and starting the curve? Like, what do those represent?
These?
No, like on the Coriolis.
Yeah, okay. So this one is the pressure gradient force. And I don't know why they've changed it. The artist wasn't careful here, but this pressure gradient, because these isobars are equally spaced, 4 millibars and 4 millibars, this pressure gradient force should be the same always in this diagram. And this one is the Coriolis force. Notice it's always at right angles to the motion vector. So when the parcel is moving in that direction, Coriolis force is like that. When the parcel is moving in that direction, the Coriolis force is like this. So you need to adhere to that when you're constructing these little cartoons, to be sure you're always drawing the Coriolis force perpendicular to the motion vector. And in this simple case, the pressure gradient force will always be towards the north because the pressure decreases towards the north. Good question. Okay. Now, this reversal in the two hemispheres, I think it's pretty clear why it happens. I wanted to show you these two satellite images of hurricanes. This one, you know where it is. There's Florida and Cuba. So this is in the northern hemisphere. Now, to be honest with you, looking at the top of a hurricane with a satellite, even if it's in motion, it's a little bit hard to tell what direction the winds are going near the surface, because what you're seeing are these high anvil clouds that are spreading out near the tropopause and covering most everything. And these clouds tend to rotate maybe in this direction near the center, but then further out they're rotating in the opposite direction. So it's a little bit complicated. So I'm not going to try to convince you that you can determine which way that thing is spinning from that still picture. I'm not going to claim that. But nevertheless, I will ask you to notice that in general, these two photographs are opposite, right? The spiral bands go off outwards and to the right here, outwards to the left below, but here, outwards to the left and outwards to the right. So that general spiral pattern is reversed in the two hemispheres. That you can see for yourself. And were you to have some data about the winds near the surface of the Earth, you would find the winds moving very rapidly in the counterclockwise direction here and in the clockwise direction there. So they really are reversed in the two hemispheres. We'll talk about hurricanes probably starting next time or the time after that, and we'll struggle with this a little bit. For example, you might ask, what would happen if a hurricane tried to cross the equator? Well, would it have to switch its direction of rotation? The answer is probably so, but it's never been observed to happen. Hurricane has never successfully crossed the equator. It would be in a foreign country, right? In other words, it's constructed itself to be appropriate with the sense of the Coriolis force in the northern hemisphere. If you tried to push that into the southern hemisphere, it would have to really fall apart and then rebuild itself in the opposite direction. That's never been seen to happen. We'll talk more about things like that when we get into hurricanes. Let's see, I was going to talk about toilet bowl mythology, right. So how many of you heard the legend of the toilet bowls in Australia? Yeah, okay. So the legend is that if you flush a toilet bowl in Australia, the water will swirl down in the opposite direction to that in the northern hemisphere. Well, I don't think that's true. I have tested it on occasion. But the problem is that the Coriolis force acting on a small scale is a rather small force, and other things may dominate. And here's what would dominate in the case of a toilet bowl or any small body of water. If you take a tank of water and fill it, and you're even the least little bit careless, you're going to be pouring the water into that off-center a little bit, and you're going to be giving it a little bit of swirl to begin with, just from the way you filled the basin. Now, when you pull the plug at the bottom, and that water begins to move towards the center and then drain out, the conservation of angular momentum will amplify whatever little swirl is in there. And so it'll end up swirling faster and faster as you draw the water out, but in the direction of the swirl that you gave it initially. And in almost every case, that's going to dominate over that weak Coriolis force acting on such a small scale. Now, this idea was tested some years ago up at the Woods Hole Oceanographic Institution. They took a large tank of water about this size and about my height, and they filled it ever so carefully to avoid swirl, but that wasn't good enough. They then lowered into it a kind of a honeycomb set of dividers that once it was down in there would stop any swirl that was existing. They then pulled it out carefully and waited for several days to get rid of any other remaining swirl. Then they pulled a plug in the middle at the bottom. And it took several hours to see it, but gradually there was a swirl observed, and it was due to the Coriolis force. In other words, as the water moved in towards the center, the deflecting force took the water that way. This one took the water that way, acting to the right of that motion towards the center, and lo and behold, they did get a cyclonic swirl. That is a counterclockwise swirl due to the Coriolis force. But I tell that story because of the extent you have to go to get that effect to dominate over the initial swirl. So don't expect to find that as you switch hemispheres. You'd have to do the experiment much more carefully. Now, that leads me to this story. So years ago, I was in Kenya, driving north to south across the equator, and there's a number of souvenir shops at the equator with signs like this out front, or other signs on the building say, "Get your equator souvenirs here." And we stopped at one of them, and the owner came running out, and before he allowed us to go in the store, he wanted to prove to us that his store was the one that was really right on the equator, and all those others we could see up and down the road were fake. And so he did a little experiment for us, you can see that, but he's got a little red plastic dish with a hole in the bottom and then a blue bucket beneath that. Now, here I am, watching him like a hawk, because this is my subject, right? So this is a little towards the end of the experiment. First he walked a few tens of yards north of the sign, and he put his finger under the hole on the red dish and poured the water into it, put a few matchsticks on the top so we could see the swirl that was developed, and when he took his finger off the hole, the water rushed out the hole, and indeed it did swirl down. He then walked several meters south of his sign and repeated the experiment, and indeed it swirled down in the opposite direction. He then went right under the sign, and that's the picture you see there. And I noticed that his protocol was a little bit different. He poured in most of the water and then waited for a few seconds, then poured in the rest, then took his finger off the hole, and the water ran right down without a swirl. He did a very nice job on this experiment. And of course, the point was that Coriolis force has one sign to the north of the equator, another sign to the south of the equator, and there's no Coriolis force right at the equator. However, I didn't have the heart to tell him that he had it backwards. Did you notice the way I moved my hand? When he was north of the equator, he had it swirling down this way. And when he was south of the equator, he had it swirling down this way, just the opposite of what the Coriolis force would do. Nevertheless, we were so pleased we went in and bought lots of souvenirs. So he won the day. But it makes my point that there is this odd situation where the Coriolis force is such a small force that you won't see it on small-scale experiments like this, because other effects, for example, this initial swirl, is going to dominate over that small Coriolis force. But on the large scale, it'll dominate. Questions on the Coriolis force? We have a few minutes where I'd be happy to take your questions about the Coriolis force. Anything? Okay. Well, we're going to switch gears. We're going to start talking about storm types. And well, I want to start out by showing you a picture that Jude gave me, our videographer in the back of the room here. In New Haven a few days ago, he took this nice shot of a mammatus cloud. We're going to be talking about thunderstorms in just a minute in this course. And by the way, if anybody else has nice pictures of clouds that you've taken yourself, don't hesitate to send them to me. I may even put them up on our class website. But that's a real nice one. Remember, this kind of cloud occurs underneath a thunderstorm anvil. So cumulonimbus builds up, hits the tropopause, the anvil spreads out, and then underneath that you get these falling pendants of cloud that take on this appearance of a mammatus cloud. Okay, but now we're going to talk about storms, and we're going to stay on this subject for a day or two. It's a huge subject. Your book is really good and voluminous on this subject, and I assume you've already read a number of these chapters. I hope you're doing that. But the tough thing is to define a storm. The word storm, what the heck does it mean? I didn't look it up in the dictionary, but my definition would be, a meteorologist's definition would be that it represents some kind of a local energy transformation. A transformation from one kind of an energy to another. For example, maybe potential energy to wind energy, kinetic energy of motion, or something like that. It's not an object. It's not a physical object. It's, in fact, the air that's involved in a storm might even be flowing through it. The air that's in a storm today, that storm may still exist tomorrow, but it may have a whole different set of air that comprises it. So it's not a physical object. It's a pattern of winds, of vertical motions, of clouds, of precipitation in the air. This is what makes it so fascinating to study, because it's a little bit, all these things are a little bit mysterious. They're not exactly objects. They're patterns of complicated fluid motion within a larger atmosphere. Now, they may be dangerous, but I don't want to define it that way. I don't want to define a storm as something that necessarily causes damage or takes human lives. In fact, in some cases, it may be the only thing that brings needed rain. Most types of storms produce precipitation in some way, and in many climates, that is the rain producer. So storms should not be considered all bad. Typically, they are short-lived, however. I can't think of any examples where a storm of any of the types I will define in just a moment exists more than 3 or 4 days. Now, there may be other storms nearby that grow as that one decays, but if you try to track an individual storm like a hurricane, or normally, a few days, and they've gone through their life cycle. Some of these have natural life cycles, and some of them just die for other reasons. And I've indicated that we're interested in climate in this course as well, but you can't define climate without understanding storms either, because the storms that occur in a particular location are part of the definition of the climate. For example, here in New Haven, we get a certain amount of rain in the summertime, and almost all of that comes from thunderstorms. We get rain in the wintertime, and almost all of that comes from mid-latitude frontal cyclones. So without knowing something about storm types, you really don't have much to say about climate either. They really are part of the recurring patterns of temperature and precipitation and wind that occur in any particular location. Any questions about what I mean by a storm then? I'm using it very broadly. Now, with those definitions, I want to break them down into 2 broad categories, convective and frontal. And convective clouds, convective storms, are those that are driven by latent heat release. We're going to talk about 2 or 3 different kinds of convective storms, but they all share the property that the energy that drives them is the heat that's released when water vapor condenses to form liquid or ice. And because they depend on latent heat release, you need to have a lot of water vapor to begin with in the air, and that means these are going to be warm season storms. Warm air can hold more water vapor, or storms that occur in the tropics where you have lots of water vapor all the time. But anyway, they're warm storms. You're not going to get thunderstorms very rarely would you get a thunderstorm in high latitudes up in the Arctic, for example. It's not unheard of, but it's quite rare. And when you do get it, it's only because there's been a big push of warm air temporarily up into the high latitudes that has allowed a thunderstorm to occur there. A frontal storm, the other broad category, their energy source is the horizontal gradient in temperature. If I have cold air next to warm air, that represents a potential source of energy because the warm air would like to rise and the cold air would like to sink. So holding them side by side is only a temporary thing. When I release it in some way, motion is going to begin to occur, and in some cases that'll develop into a frontal storm. I say cold season because, remember, due to the tilt of the Earth, it's in the wintertime in mid-latitudes when you've got the big differential heating. The pole is getting no sunlight, the equator is getting a lot, and so it's in the cold season of each year for the respective hemispheres that you get the strong temperature differences, which will then allow frontal storms to form. Now this is easy to remember because the definition of a front itself is as a region of strong temperature gradient. So it's easy to remember what is the energy source for a frontal storm. So first we're going to talk about convective storms. And I'm just going to talk about three: air mass thunderstorms, severe thunderstorms. Your book does a good job on these. I'm not going to say much about the different types of severe thunderstorms, but there are subcategories within the general domain of severe thunderstorms, and then hurricanes fall into that category as well. So what I'm saying is that all of these storms are driven by the energy from latent heat release. And remember, that number is about 2.5 million joules per kilogram of water vapor. So for every kilogram of water vapor that you condense, you get 2.5 million joules of energy added to the atmosphere in the form of heat, but then that may make that air rise, and that'll get the whole storm going. So it all goes back to this rather large latent heat that's present when water vapor condenses. So the first and the most benign of these is the air mass thunderstorm. It's called an air mass thunderstorm because basically there's a property of the atmosphere that will allow them to form. And so when we say that a warm tropical air mass has moved into New England with the properties of being warm, not very stable, and not very strongly sheared, then thunderstorms can occur. So we're kind of included here the fact that it's the nature of the air mass that is going to control whether or not these thunderstorms occur, and that's why they're called air mass thunderstorms. So they go through a life cycle. They start as a fair weather cumulus cloud, but there is enough water vapor in the atmosphere so that as, excuse me, as the air begins to rise, the latent heat addition is sufficient to keep that air moving upwards. It'll keep going under many circumstances all the way until it reaches the tropopause. It'll flatten out at the tropopause, maybe overshoot a little bit, but generally flatten out. And about the time it gets there, it'll start to rain heavily out the bottom. The process by which the rain drops are made is almost always the ice phase mechanism in these clouds. Remember, it may be very warm at the surface. After all, this is a summertime phenomena. But nevertheless, because it gets colder as you go up, and here's the 0 degrees Celsius line, once that cloud gets above the 0 degrees Celsius line, you've got supercooled water that'll then start the ice phase process going to generate, at first, snowflakes. Then they'll melt as they fall, and they'll fall as rain out the bottom. There may be some lightning coming out of those clouds. If they are moving rapidly across the landscape, they will just give you a brief shower, which won't be too much of a problem. If they happen to be stationary, even though they may only last for an hour, if they're stationary, they might cause some local flooding. So whether they cause flooding depends not only on the rain rate from these systems, but how fast they're moving across the landscape, whether they're distributing that rain as they move. There might also be some, of course, the lightning can cause damage. You could be struck by lightning or could cause a fire, but normally these are not so damaging. In fact, they bring us most of the summertime rainfall that we count on in New Haven and most of the rest of the world. In the warm season or the warm climate zones, this is the primary rain producer. So it's definitely a positive thing. Questions on air mass thunderstorms? I'll show you the distribution of these in just a minute. But first I want to start talking about the severe thunderstorms. Now, severe thunderstorms require some of the same ingredients. You need to have a warm, moist atmosphere, no strong inversions, because you got to get the air moving upwards. But the additional element determining that you will get a severe thunderstorm instead of just an air mass thunderstorm is wind shear in the troposphere. And here they've drawn up on the right axis, the artist has drawn in a sense of that, some low-level southeasterlies, weak southeasterlies near the surface of the Earth, turning to a jet stream from the west aloft. That's the kind of shear I'm talking about, shear across the whole tropopause. So now instead of getting this thunderstorm building up and retaining a kind of symmetry, instead, as it builds up, it gets tipped over by the shear. And that changes everything. Let me go back. I forgot to mention something which is needed now in this argument. So let me go back here for a moment and point out to the fact that the air is rising, is generally converging into this storm until the rain begins. Sorry, I forgot to mention this. This is important. Once the rain begins, the rain falls below cloud base into air that has a relative humidity less than 100%, and some fraction of the raindrop water mass is going to evaporate before those raindrops hit the surface. That evaporation causes some cooling in this area. And once that is well established, the cooling by evaporation of raindrops, that cool air begins to fall to the surface and spread out. When it does that, it shuts off the inflow. Here we needed inflow to keep that cloud going. Once the downburst begins, once the cool air begins to flow down and out, the supply of warm air rising is cut off, and this storm dies. And normally that whole sequence takes between an hour and 2 hours, and then it's gone. There may be other thunderstorms popping up in the vicinity, but this one has a very short lifetime, typically less than 2 hours, and it kills itself off. It's a form of suicide where the rain that falls out the bottom partially evaporates, causes cool air, which rushes down to the surface, spreads out, and cuts off the inflow to that storm. You will feel that. If you are a few miles away from this storm, you might hear the thunder coming from the lightning, and then several minutes later, there may be a cool gust of wind that comes to you from the direction of that thunderstorm. That's this cool air falling out of the bottom of the cloud. So watch for that, because if you're aware, you can tell the outflows coming from each of these storms as it progresses through the afternoon or the evening. You'll feel these outflows reaching you. Now, what's different about a severe thunderstorm is that because it's tipped over and made more complicated, the inflow continues on one side of the storm, while the rain and the outflow is on the other side of the storm. They don't cancel each other. Because it's sheared in this way, you get air coming in from the back that gets caught up in the rain, brought down to the surface to form the cool air in the gust front. And then out ahead of the gust front comes the warm air, which is the fuel for the thunderstorm, that'll rise up in this way and spread out to the right and a little bit to the left. So the downdraft caused by evaporation and the updraft, which is generating the cloud, they're not in the same place. So they don't cancel each other. So this can be a long-lived storm. This can exist for many hours, just trucking across the landscape, sucking up air from one side, spitting it out the back along with rain, and continuing to kind of move along like that until conditions change, until it encounters air that's too dry or whatever might change might eventually kill the storm. But it could even last overnight. In other words, it could start this afternoon and the same storm could exist through the night, in some cases even into the next day, because it doesn't have a way to naturally kill itself off. Also, these are much more severe. They are broader in extent. The updrafts are quite a bit stronger. Instead of being 2 or 3 or 4 meters per second updraft, they could be 10 or even 15 meters per second updraft speed. And this gives rise to a whole set of new dangers that come along with this storm. Here's a picture of one. The updraft is back in here, coming right up through there, and there's the rain back in the rear. The anvil, you can't see the top of it, but the anvil is up here somewhere. There's one from a distance. We can't see much. I think this is where the air is coming up on this side. The rain is back here. There's the anvil spreading out. Yes?
What drives what direction the storm moves?
So it's going to move by the direction of the winds in the middle of the troposphere. Typically, the winds around 500 millibars will determine how that storm moves. That's a good question. So normally from west to east, but it'll depend on the local conditions. Could be in some other direction if the regional winds are from a different direction. Here's a picture from space showing the anvil. Clouds popping up on this side. And okay, so this list is probably not inclusive, but I want to mention at least these things. What damage do you get from severe thunderstorms? Well, heavy rain and flooding. The rain rates can be very high, and again, if the storm's moving slowly, that's the most dangerous situation because it'll put a lot of water into each watershed. Because the updraft speeds are so large, and there's a lot of supercooled water above the 0 degrees Celsius line, you can develop riming, which will then grow and grow and grow, and that hailstone can be suspended for maybe 15 or 20 minutes, even as it grows, because of the very strong updraft speed. So it'll continue to grow until it finally gets too big, and then it'll finally fall out. But by that time, it may be quite a chunk of ice that has grown by riming, and then as that falls to earth, it picks up a lot of speed, and that could cause damage to crops, buildings, or people. There will be usually hundreds, if not thousands, of lightning strikes from these severe thunderstorms, and that's a real danger. So these are big lightning producers. Your book describes how lightning is produced. It has to do with ice crystals bouncing into each other and then being carried off by different vertical motions. When they strike into each other, they separate charge. And electrical charges of one sign get carried up, developing a big voltage difference between the upper part of the cloud and the lower, or the cloud in the ground, and then you get, when that breaks down, you'll get lightning strikes. Tornadic winds. Tornadoes are formed by severe thunderstorms. This is a very important aspect of them. Unfortunately, one of the least well understood. There have been a number of recent field projects, one just summer of 2010, in which once again we mobilized dozens of radars on mobile trucks and all kinds of sophisticated instruments to try to measure tornadoes at the moment of generation. So difficult to do because they're random and they're hard to predict. So how do you get the trucks and the people and the instruments together right at the point where that tornado is going to form? We're working very hard at that, and the literature on this is fascinating. People are being so clever about developing new ways to do these measurements, and yet today we don't quite understand how tornadoes form. We do understand this, however, that these large, severe thunderstorms generate a slow rotation within them. That's called the mesocyclone, or the mesovortex. We understand how that forms. But that's a slow, large-scale vortex. It might be 40 or 50 kilometers across, and with wind speeds of only 4 or 5 meters per second. That certainly isn't the tornado itself. But it may be that somehow that rotation gets amplified near the surface of the Earth in certain spots that would generate tornadoes. So it may be the mesovortex is the precursor of the tornado itself, but that's one of the things we've been unable to determine with scientific certainty. So this is a very open question, and I'm not going to say much more about it, but if you want to dig in and read about this, there's a lot going on in research meteorology today to try to understand that question. Now here's another issue that I'm going to mention and then drop it, because there is, speaking of toilet bowl mythology, there is a little bit of mythology here. Some people will say, if a tornado is approaching your house, you should open the windows. And the reason for that is that there's low pressure in the center of a tornado. We know that's true. And if this low pressure center suddenly moves over your house, you've still got high pressure inside your house, low pressure around it, and your house will explode. And the way to prevent that, of course, is to open the windows so the pressure can equalize more rapidly. Well, that little bit of advice has been around for many, many years, and but I know that the recent recommendation from the National Weather Service is that that probably is not valid, or at least it's not. You probably, by opening the windows, the chances are you'll do more damage to your house than by keeping them closed. Either the wind will come in or rain will come in and you'll get damage that way. There's no real strong evidence that this pressure difference has an effect on exploding your house. So I'm not going to say anything categorical about this, except that generally this is not considered to be part of the story. But I will say this one, the gust front winds, so that cool air that's generated by evaporation below cloud base will fall to the surface of the Earth and then spread out at speeds that can almost approach the speed of the tornadic winds. So the first thing that a meteorologist will do when there's been a severe thunderstorm and damage has been reported, he'll get in his car or he'll get in a helicopter and he'll scout the area and try to figure out, was the damage due to the gust front winds or from the tornadic winds? That's question number one whenever these kind of storms occur. Can you separate the damage caused by that cool downburst of air from the damage caused by the tornado itself? We're out of time, but we'll continue in this theme on Wednesday. At station, the 500 millibar surface is 5,870 meters above sea level. The temperature is 27 Celsius, and the dew point is minus 11 Celsius. So each of those balloons, as they cross that surface, you have the data there, and then the contours are laid on by the computer. The winds are given too in a little wind barb, using the convention of a short feather being 5 knots, a long feather being 10 knots, and a thick feather like that being 50 knots. So we're talking about geostrophic balance, and I showed you a diagram like this last time, but I wanted to bring it up to date by showing you the current one. So this is the soundings again from last night. It shows this rather interesting little circular pattern over the East Coast. And if you look at these values, 560, 550, I guess 549. So this is a low pressure center. So this would be called a cyclone. It's not at the Earth's surface necessarily. It's at the it's about 5 kilometers up in the atmosphere, but that would be a cyclone. So higher pressure around it, lower pressure in the center, and just like we derived theoretically, the winds go counterclockwise around that because we're in the northern hemisphere. And notice how well the winds parallel the isobars. And so these conclusions followed from the geostrophic balance assumption. And the closer the isobars are together, the stronger the wind will be. Here's another system over the west coast, a strong jet stream coming up here, winds reaching to about 65 knots where the isobars are closer together, and then where the isobars are further apart, the winds are considerably weaker. So those general rules about geostrophic balance are seen to hold on this kind of a diagram. Are there any questions on this one before I go back to the main lecture? So these maps are easy to find, and I encourage you to check in with them from time to time to see what's going on. Let me just get rid of this and go back to where we were. Yeah, let me just go back for a second. So we're in the geostrophic discussion. I showed you these little bullet points about geostrophic force balance, these formulas we went through. This is the map that I showed you last Friday. This was from that moment. And of course, things have changed a bit between now and then. It may be that that same trough is the one that slid east and become a cutoff cyclone the way we saw, or maybe some other thing happened between the two dates. But I suspect it's just that slid over to the east and filled out to form a full round cyclone the way we saw. I think I ended with this one, which was just an example of an isobaric map at the surface of the Earth. These values are sea level pressure. So wherever the pressure was measured, it was reduced to a common altitude, sea level, and then the contours were laid on it. So you can use this to analyze then. And here we had an anticyclone and a cyclone. There are no winds given on this, but now, knowing the geostrophic law, we can say quite a bit about this. The only problem is that this is down close to the surface of the Earth, or in some cases even below the surface of the Earth. It's kind of a fictitious, there's no, these mountains are a kilometer or two above sea level, so producing a sea level map is a little bit odd for that, but that's okay, we can still interpret it. But the other problem is that when you're right down near the surface of the Earth, there is some friction added to the winds as well. And that will break the geostrophic constraint. Maybe not too badly, but it'll break it a little bit. What tends to happen when you're near the surface is that the winds, instead of blowing right along the isobars, tend to rotate in a little bit. So they're mostly going along the isobars, but they're crossing it a little bit from high pressure to low. So the winds tend to rotate a little bit like that. That's something, that subject is called the Ekman layer. The Ekman layer is a description of how those winds turn in the boundary layer. And when you're analyzing your pilot balloon data in the lab, in lab number 2, you might find some hint of that, some rotation of the wind in the boundary layer due to that breaking of the geostrophic law due to friction. So keep, you may not see it or you may see it, but keep an eye open for it in that data that you're analyzing from from your data from the pilot balloon launch. So what more can I say? Well, we're going to be talking about mid-latitude cyclones probably next time, and this is an example where, in addition to sketching in the isobars, they've also drawn in their interpretation of where the cold fronts and the warm fronts are on this particular day. But that's more of an interpretive thing. The isobars are just cut and dried. If you know the pressure data, you can contour those in. If you expand out to look at most of the northern hemisphere, you can see that at any given time, there are lots of highs and lows, cyclones and anticyclones. And again, no wind is given on this, but you can get a pretty good idea of what the wind is. Each one of these lows has a wind going around this way. Each one of the highs has a wind going around that way. And the speed of the wind is related to the packing of the isobars. So the mid-latitude and the high-latitude atmosphere is just loaded with these eddies. And one of their jobs is to pump heat northward to balance the heat budget of the high latitudes and low latitudes, which I spoke about last time. If you go to the southern hemisphere, here's Australia. Of course, now everything is backwards because the Coriolis force is reversed in the southern hemisphere. It acts to the left of the motion vector, and so those relations. Well, we're getting into weather, and so I'm going to be paying a bit more attention to what's going on around us. And this is a weather map from the 0Z soundings. In other words, the soundings, the balloons that were launched yesterday evening at 8 p.m. here would be 0Z Greenwich time. And each of these little clusters of data represents a balloon that was launched. And this is the 500 millibar map. So when data is analyzed above the Earth's surface, it's normally done on constant pressure surfaces. It's not exactly constant altitude, but it's more or less a flat horizontal surface. And what's contoured in black is actually the altitude itself. So that constant pressure surface is a little bit rolling. But the thing to understand is that the level of constant altitude on a pressure surface is very much analogous to an isobaric curve on a level surface. So you can think of these as isobars, these heavy black lines. The temperature, lines of constant temperature, the isotherms, are in the dashed blue lines. But the data from which it is all derived are these little clusters. So there is to the right of the symbol is the altitude of the 500 millibar surface with 1 0 left off. So that at that